So in this problem, we have a hypothetical solar system where the planets orbit in circular motion, and the ratio of any two periods of two planets is proportional to the ratio of their orbital radii squared. And we're asked to figure out the dependence of the central force on the distance of the planet from their sun. Now, if we assume that the central force is the only force acting on a planet, then by Newton's second law we have that the central force, which we will call F of r, where r is the radial distance from the sun, that's going to be given by the mass of the planet times its its radial acceleration, which is going to be given by omega squared r. Now, we know that omega, the angular velocity, or the angular, omega, which is the angular velocity, is equal to 2 pi divided by the period, big T, of the orbit, which means that omega squared is equal to 4 pi squared over big T squared, which is also equal to F of r over mr, which comes from the first equation. Now this means that F of r is equal to 4 pi squared mr over t squared, big T squared. So from this equation we see that the radial dependence of the force is given by r over t squared. Now, since we're given that the ratio between any two periods, let's call them T1 and T2, the ratio is proportional to the orbital radii, the ratio of the orbital radii squared. So let's call it R1 and R2, which means that the period of any of the planets in the hypothetical solar system is going to be proportional to their orbital radii squared. So we have that t is proportional to r squared, which means that t squared is proportional to r to the 4, which means that the force, which is proportional to r over t squared, is going to be proportional to r divided by r to the 4, which is equal to r to the negative 3. This means that the central force is going to be proportional to r to the negative 3, which is our final answer.